So 9.2 is the first section in this unit where we actually get into doing a specific significance test. It will follow very parallel to the order of the intervals that we did last unit. So the first one we're going to talk about is a test for one proportion, also called the one proportion z-test because proportions are always z. So just to fill in a few more little details for the state plan to conclude for one proportion test specifically, your state step, your null will be that p, notice no hat because we're talking about the population, p is equal to whatever the value is. The alternative will be that p is either less than, greater than, or not equal to that same value, and then define the p. For plan, you're going to name the type of test. This will matter more later when we have multiple types of tests we're doing at the same time. But for this, it'll be a one proportion z-test, or a z-test for one proportion would be fine as well. Our plan step, our conditions, otherwise, it will sound very similar to confidence intervals. So we have either random sample or randomized experiment is needed. Our normality is that n times p naught. Now notice that we are not using p hat here. We used p hat for confidence intervals because we did not have an idea for the population. Here we do. We have p naught, which is whatever is in the null hypothesis. So if that is our idea for what is true about the population, so in the last class, if we think that the proportion really is 80%, then we would do the sample size times that 80%, and the sample size times 1 minus that 80%, and make sure both of those were greater than 10. Regardless of what the p hat is, I would use the p from the hypotheses. For independence, if it is a sample, you can, of course, use the 10% condition, and then if it is an experiment especially, you would need to make some statement regarding that the response of one subject should not affect the response of any other. For our do step, we will calculate a test statistic in addition to the p-value mentioned last class. Our test statistic formula is the p hat, so that's the sample value, minus the p from the hypotheses, over the standard error. Notice once again, this is a very similar standard error formula to what we had for the confidence interval, but since we have a p that we think is true, we'll use that instead of p hat. So confidence intervals, standard error was all p hats. Statistics, the hypothesis test, you will use all p naughts. So p naught, 1 minus p naught over n under the root. And then we'll conclude, we'll fail to reject or reject the null, and then conclude in context. So we either can support the claim or we don't have enough evidence to support it. So back to the potato example from last section. To fill in a few more details, we have a random sample of 500 potatoes that are selected from a truck and reveal that 47 of those 500 have blemishes. Carry out a significance test at the alpha equals 10% significance level. That means 10% will be our cutoff, where we say if it's below it, we will reject the null. What should the producer conclude? Notice that producer may choose a higher significance level if they want to be more likely to reject. Okay, so anything below 10% they're going to reject. So if the factory is trying to be cautious and not take in potatoes that they're not going to be able to use, they would select a higher significance level. So we're going to test the hypotheses, either p is equal to versus p greater than 8%, because the 8% is, if it's more than that, they're not going to be able to be used by us, and to find the p, where p is proportion of the truckload of potatoes that have blemishes. Plan step, we're going to do a one proportion z-test. The sample was randomly selected, okay, and can be considered independent since 500 potatoes, it is reasonable to think that is less than 1/10 of all the potatoes on the truck. The normal condition is met because the n times p, so 500 times 0.08 and 500 times 1 minus 0.08 are both greater than 10. We calculate our p hat here since we'll need it for our z-test statistic. So our p hat was the 47 out of 500, gave us a 9.4 sample. Notice that is bigger than 8%, but that doesn't necessarily mean the whole truck has a larger than 8% blemish rate. So we'll see if that is high enough to make us suspicious. So the test statistic in this case is z is equal to the sample proportion minus the null proportion over null proportion times 1 minus the null proportion over 500 under the root. That gives us a z-score of 1.15, so 1.15 deviations above average. Look at the table A value since it is a z-score, and since it is the right-hand tail, we'll take 1 minus the value from the table and get the p-value of about 12.5%. Okay? Since our alpha value was 10%, this is larger than alpha. P is larger than alpha. We would have to fail to reject the null. And since we're failing to reject, it's not saying we accept it. We never accepted it, but we don't have enough evidence to prove it wrong. Therefore, we cannot conclude that the proportion of Flemish potatoes is more than 8%, even though our sample was a little bit more. Or another way of saying it, we do not have enough evidence to conclude that the proportion of Flemish potatoes for the whole truck is more than 8%. Okay, so type 1, type 2 errors we talked about back in 9.1. We want to take that just one step further because we concluded that we would fail to reject. Which error could we have made? Well, the failing to reject incorrectly was a type 2 error. So because our conclusion was fail to reject, we could have made a type 2 error, though we don't know if we have or not until we get the truckload of potatoes out of the truck. Here are the calculator notes. In the calculator, just like for confidence intervals, you go to stat, tests, and we're going to look at the tests instead of the intervals, so you actually don't need to scroll. One proportion z-test is number 5. Okay, so we would put in our null proportion was 8%. Then 47 out of 500 of our potatoes had blemishes from our sample. Our alternative is greater than. This is greater than P naught, which is defined up here as 8%. So greater than 8% is our alternative. Hit enter. There is your Z value, and there is your P value. Okay, so we had a Z test statistic of 1.15. P value is about 12.5% or 12.4%. Okay, if you choose to do the calculator way, just listing what you have written in your calculator will not give you partial credit, so make sure that you type things in correctly or write the formula down, but then use the calculator to actually calculate the p-value if that's quicker for you. You would need to record, in either case, whether you use the formula or the calculator, you need to record the z-test statistic as well as the p-value. Okay, take a minute and think through this example. See if you can do the state plan to conclude steps for it. According to the Centers for Disease Control, 50% of high school students have never smoked a cigarette. Student Taeyeon wonders whether this is true at his large school. For his class project, he surveys 150 students at the school, gets a response from all of them, and 90 of them say they've never smoked a cigarette. What should he conclude? Give appropriate evidence to support your answer. So notice it doesn't say do a hypothesis test, but that would be the option we're going to choose. It also does not give an alpha value, so you can choose one. You can use the 10% again, or like our book does, do the 5% fallback default significance level. So go ahead and pause the video for a minute and try working out the steps to this one on your own. So the state step, I wish to test at alpha equals 5%. The hypotheses of null is P is equal to 50% versus the alternative P is not equal to 5%. Taeyeon just wonders whether this national result holds true. It doesn't say that Taeyeon thinks it's going to be greater or less than, so just not equal to, where P is a proportion of students at his school who have never smoked a cigarette. Still the one proportion z-test. The sample was a simple random sample. It can be considered independent as long as 150 is less than 10% of all students, which seems reasonable since it's described as a large school. The normal condition is met because N times P, 150 times 50% is 75. Notice the same here since it's 50%. Our p-value is 90 out of 150, 60% had never tried a cigarette. Plug that into the z-test statistic, get a z-test statistic of 2.45, and then go to the chart. So you could either, here's positive 2.45, go to the chart, look up the value and subtract from 1, because the chart, of course, is going to give you the proportion to the left, and we want the tail proportion. So if you do 1 minus the value from the table, you get 0.0071. You can also, especially since this is a two-tail test, meaning we're going to have the tails on both sides, do the symmetric tail. So if this is positive 2.45, this value over here is negative 2.45, look up negative 2.45 on the chart, and it would give you 0.0071, and then multiply either case, whether you do 1 minus this value or just do this value, do 2 times the number you get to combine the area of the two tails, and you get a combined area of about 1.4%. So since P is less than our alpha, which we chose 5%, we would reject the null. So in other words, we say that the null is incorrect. And we can conclude, or there is significant evidence that the proportion of non-smokers at Tejon School is different from the CDC national proportion. Okay, in this case, because we rejected the null, we could have made a type 1 error, because the type 1 error is defined as rejecting the null incorrectly. Here is the calculator version of this, connecting confidence intervals with two-sided tests. A 5% significance level should give us the same result as a 95% confidence interval. Notice that we have a 95% confidence interval with Tejon's data. We would get that the true proportion is somewhere between 52% and 68% if we rounded. Since 50% is not within that interval, from last chapter, that would suggest to us that 50% was not true for Tejon School. To carry that over, that is most helpful comparing the result from a confidence interval with a significance test if it is a two-tailed. So this was our notation for if and only if. It's calculus notation. So if it's a not equal to alternative hypothesis, that's the only time you have to do a two-tailed test where you calculate the area of one tail and then double it. And that is when you will most easily get the same result as a confidence interval of the complementary percentage. So if I have a 10% significance test, that should give you the same result as a 90% confidence interval, because 90% in the middle would have 5% on either side, which would add up to 10%. A 95% in the middle would give us a total of 5% in the two tails together. 99% in the middle would give us the same result as 1% in the two tails together. It is possible to do it otherwise. If I have a one-tailed test, for instance, 5%, then I would have to figure out, okay, there's 5% in the other tail, which would be 90% in the middle. So it would be possible, but it's a little bit more work if you have just a one-tailed test. So once again, to sum that up, intervals in some ways are better. They not only allow you to evaluate whether there is a difference between what was believed and your sample results, but they also give you an estimate for a parameter when no estimate previously existed. But hypothesis tests are a little bit more widely accepted because they are the I believe, older and more standard method for determining whether a population parameter is true. And it is maybe a little bit a step easier if you have just a one-sided test. In rare instances, and this does not come up often, different conclusions could be drawn between an interval and a significance test, even when these percentages do hold true, and that is only because the confidence interval uses p hat in all of its calculations, whereas the hypothesis test uses p naught in some of them. But that does not happen often. When this AP free response says to provide statistical evidence, like it did for the Tejon example, you could actually use either an interval or a test, whichever you feel is most appropriate. Once again, using them interchangeably, better if you have a two-sided test. In general, when it says provide statistical evidence, the most standard response is to do a significance test. One last thing for this section for our video is the computer output. Notice it gives you the sample size and the n, and sometimes the standard deviation. as well as the z-value and the p-value for the test.